In this final video on wind energy, we will discuss some emerging technology in wind energy harvesting. By the end of this lecture, you should be able to enumerate key concepts in offshore wind energy, identify several types of high-altitude wind harvesting devices, recognize a few innovative designs in VOTs, list emerging multi-rotor wind turbine concepts. Wind energy has become a key player in the global transition to renewable power. While horizontal axis wind turbines still dominate today's energy landscape, several emerging technologies are being developed to push the boundaries of efficiency, flexibility, and deployment, especially in challenging or unconventional environments. In this final lecture on wind energy, we will take a brief look at four promising directions: offshore wind, airborne wind energy, vertical axis wind turbines, VOTs, and the multi-rotor system. As we learned in the wind resource session, offshore environments typically offer stronger, more uniform, and less turbulent wind due to the flat sea surface. Offshore wind is already a rapidly growing sector. However, it also faces notable challenges, including higher installation and maintenance costs, complex logistics, and so on. Despite these hurdles, continued innovation in foundation design and floating platform is steadily expanding the feasibility and the reach of offshore wind power. Historically, offshore turbines have been installed in relatively shallow waters up to around 30 meters deep, using monopile foundations, which are essentially extensions of the turbine tower. Gravity-based foundations have also become more common. These near-term concepts are shown on the left. On the right, you can see several floating foundation concepts that are more suitable for deeper waters. These include spy buoy platforms and tension leg platforms, which allow turbines to operate in waters far beyond the depth limits of fixed bottom foundations. Airborne wind energy aims to capture stronger and more constant winds at higher altitudes without relying on tall towers. These systems typically use tethered flying devices like kites to generate electricity either on board or via the tether connected to a ground-based generator. Their key advantages include reduced material usage compared to conventional turbines, access to higher altitude wind resources, easier deployment in remote or offshore locations. Although still in the early stage of development, several companies have demonstrated promising prototypes as shown in the images on this slide. Unlike conventional horizontal axis wind turbines, vertical axis wind turbines, or VOTs, rotate around a vertical axis. They offer several potential advantages. They can capture wind from any direction without needing your control. They are less sensitive to turbulence than HOTs. They may generate lower noise due to the relatively lower rotational speed. These features make VOTs ideal for urban and turbulent wind conditions. Their lower center of gravity is particularly beneficial for floating applications, with the mechanical and electrical components positioned near the base, reducing both installation and maintenance costs. This slide shows a few innovative VOT prototypes. The deep wind concept on the left, which uses the sea itself as a bearing to support rotor loads. The twin float designed by Nenufer in the middle, which mounts two VOTs on a single floating platform to reduce cost. The X-rotor concept on the right, where a large X-shaped vertical axis rotor generates motion and increase the apparent wind speed seen by the two small horizontal axis rotors at the bottom tip of the X rotor. To enhance power extraction, as well as to gain benefits in standardization, scalability, and operational flexibility and land or sea use efficiency, various multi-rotor concepts have been proposed. The photo on the left shows a co-axis dual-rotor wind turbine, which has been prototyped. Studies have shown that co-axis dual-rotor wind turbines can increase power production by approximately 7% to 20% compared to conventional single-rotor system. The center images shows Vestas' prototype of a 2x2 planar multi-rotor system. Tests and simulations have demonstrated that this configuration can improve power output by up to 2% at below rated wind speed. On the right is the wind catcher concept developed by Wind Catching System. This is a floating multi-rotor wind solution designed to reduce the cost of energy for offshore wind. Its unique layout aims to maximize energy capture in a compact footprint, particularly in deep water environments. Perfectly integrated with the multi-rotor system, our team at TU Delft has introduced the concept of using lifting devices, specifically high lifting wings as shown in the picture. These devices can redirect the wind either upward or downward, depending on their placement and configuration. By modifying the vertical flow field, they enhance the vertical entrainment of high energy flux from the upper atmosphere into the wake region. This accelerates the edification of momentum, promoting faster wake recovery and improving overall power performance within a wind farm. This concept has been validated both numerically through high-fidelity simulations and experimentally in wind tunnel tests. Remarkably, the available power nearly doubles, rising from around 40% in the reference case to approximately 80% after installing the lifting devices from the second row. In other words, power losses due to the wake interaction are reduced from roughly 60% to just 20%, highlighting the potential of multi-rotor system with lifting devices to significantly outperform conventional wind farm layouts. The video on the right shows a prototype demonstration of such a multi-rotor system with a lifting device. In this lecture, we have explored several emerging technologies in wind energy, including near-term and long-term concepts of offshore wind, airborne wind energy system for harvesting high-altitude wind, several innovative vertical axis wind turbine designs, concepts of multi-rotor system to enhance power extraction and scalability, integration of lifting devices with multi-rotor system to improve wake recovery and wind farm efficiency.